All right, guys, we are jumping into a section called conics, which is really just about a lot of different shapes. We've actually kind of done conics already. In circles, conics are just basically a certain group of shapes. We're going to, again, be looking at a bunch of them, and I want to start today with one of the first that we'll look at called an ellipse. So an ellipse is kind of a mathematical term for, I'll basically say, an oval. So basically, we're going to be looking at oval shapes and what their equations of their graphs look like, what do the graphs look like, and a whole bunch of things about them. Okay, so I kind of defined an ellipse as an oval-like shape where this, here's the key part, I'll kind of show it in a minute. It's an oval-like shape where the sum of the distance between points on the shape and 2 points inside are the same. Okay, so where points, the sum of the distance between 2 points on the inside and a point on the circle or the oval are the same. Okay, and these 2 points, okay, on the inside are called the foci. F-O-C-I, the plural of focus. All right, so you may be a little bit confused by that definition. I will do my best to explain this over the iPad here. But there's actually a cool little thing we can do in class, we'll do in class tomorrow, that really kind of drives home this point. So basically what it's saying is, all right, what I just did in red are my foci. I have 2 points inside the oval. And what it's saying is it's saying that the distance between those 2 foci to any point of the circle, or the sum of those distances, are always the same. So if I pick a circle here in blue on the ellipse, okay, there is a distance in which I'll mark in green, okay, between the red foci there and the red foci there. It can almost forms a right triangle, it doesn't have to. Okay, and let's just say, for instance, that the distance from that foci to the point on the ellipse is 7, and this is 3. Okay, they sum to 10. Okay, what it's saying is that as I move this blue circle around, so let me pick another random point. Let's say I have another random point over here on the ellipse. If I take the distance between the 2 foci, or the sum of the distance, I should say, I don't know, maybe call that one 9 and that one 1, the sum, notice, is equal to 10 again. And basically what this saying is, what makes an ellipse is basically if you take the distance between those 2 red foci to any point on this ellipse that I'm dotting in blue, the sum of their distances is always going to be the same. It doesn't always have to be 10, it always has to be the same. So again, let me choose yellow now. The sum of the distance between here and here, I don't know, maybe it's 8 and 2, but no matter what, where that point is on the ellipse, the sum of the distances between the 2 foci to that point always must be the same thing. Okay, so it always must be the same thing. That's what an ellipse is, and I have, you might say, well, that doesn't really make sense, or like, why is that the case? Again, I have a kind of this really cool thing we can do on the whiteboard tomorrow that will really show you like how this works. It's kind of cool. But for right now, that's our technical definition. Sum of the distances between the foci and a point on the ellipse is the same, okay? All right, so how do we represent this shape using an equation? If we were in school right now, I would probably make us do a proof of this. The proof is a bear and a half, so I don't want to go through it. The solution to the proof for how we get the equation is on Canvas. So if you are interested in it, you can certainly feel free to look that up. But let's first go over just a little bit of vocab. So what I'm going to do here is just draw myself another ellipse. Let's see who's got some good ellipse drawing here. I'm not going to be very good here. Okay. Let's say that's, oh my lord, that's, I'm not even going to accept that. Let me try another ellipse. Hard to do this on the iPad. All right, that's a pretty terrible ellipse. Okay, but the center of the ellipse is going to be at 0, 0. So this ellipse is centered at 0, 0. So let's go over a few vocabulary points. So notice this ellipse is situated sideways, that the longer side or the longer um, part of the ellipse is going sideways, right? So we call those points that are kind of at the end of the long part of it the vertex. Okay? We call those 2 points the vertex. And then the 2 points, let me do in green, between the two shorter sides or shorter ends, again, depending on how it's oriented, is called the co-vertex. So there's the co-vertex. So the distance between the vertexes or the vertices is always going to be longer than the distance between the two co-vertices, right? Okay. The axis, I'm going to go back to red here. Okay. The axis that the two vertexes are on is what we call the major axis. Okay. So the vertices will always be on the major axis, and the co-vertices will always be on what we call, okay, you probably can guess it, the minor axis. Okay. So we have the major axis, that's where the vertices are on. The minor axis is what the co-vertices are on. And I'm kind of running out of room here, but those dots in blue are my foci. Those are like the special points that the sum of the distance between those 2 points and any point on the ellipse are the same. Okay, those are the foci. The foci are always, okay, they're always on the major axis. Okay, so they're always on the major axis there. Okay, and again, this is centered at 0, 0. So the only thing we're looking at right now are ellipses centered at 0, 0. We'll look at ellipses later on that are centered other places. Now, just to drive home here, okay, or actually before we do that, let's maybe go over the equation. So again, the proof of this equation is in on Canvas, but again, I want to save us some time. The proof is a bear. The equation of this ellipse above, okay, my equation is going to be x squared over a squared, and I'll explain what a and b are in a second, plus y squared over b squared equals to 1. Okay, so x squared plus x squared over a squared plus y squared over b squared equals 1. So one thing I didn't say above, but I'll say now, and I did this on purpose, is that the coordinates of my vertex is going to be a comma 0, and the coordinates of my other vertex are going to be negative a comma 0 when I'm centered at the origin. So a represents the distance between the vertex, okay, vertex a equals distance between vertex and center. Okay, the two co-vertices points are 0 comma b and 0 comma negative b. So b equals the distance between the co-vertex and center. Okay, so that's what the a and b represent in the equation. X and y are your variables, and notice it's equal to 1. Okay, the other conic we've seen this here is a circle. Circle is equal to r squared. Okay, an ellipse, it's always equal to 1. Okay, it's always equal to 1. Now notice this is when, okay, we have a horizontal ellipse. But what, if I just scroll down a little bit more, what would happen if I had, draw another axis, and then let me draw another horrible ellipse or oval. Maybe if I draw it this way. Nope, still terrible. But if I had a vertical ellipse, my vertices would now be here and here. Again, they're always the longer of the two lengths. And my co-vertices, okay, would be on the x-axis here. So the major axis would now be the y-axis. The minor axis would be the x-axis. This point here would, oops, let me go back to another color. Okay. This point here would now be 0, comma a, because a always represents the vertex. This point here would be 0, comma negative a. Okay. This would be b, comma 0, and negative b, comma 0. So the equation of my ellipse in this case would be x squared over b squared plus y squared over a squared equals to 1. So that's when it's vertical. Notice the a and b switch. So this is horizontal. This is vertical. Okay. So the question might be, let's say you get an equation like, hey, here's an equation of ellipse, x squared plus 16 plus y squared over 25 equals to 1. Okay, and let's say the circle, the ellipse hasn't been drawn out. How are you going to know, is it a vertical ellipse or a horizontal ellipse? Well, think about this. What value is going to be greater, a or b? Well, if a always represents the distance between the center to the longer part of the ellipse, okay, a always needs to be the larger number. So wherever the larger value is underneath, so in this case 25 is larger than 16, it's underneath the y, that tells you that the a value, that this is a vertical ellipse, and the a value would be 5. Okay, so it's a vertical ellipse, so you're going to know it's vertical or horizontal depending on whether depending on which number is greater. Okay, so if it's greater underneath the x, that means it's a horizontal ellipse. If it's greater under the y, it's a vertical ellipse. Okay. All right, so let's go to the next page here. Some things to know. Again, a is always the larger number. We talked about that. Okay, the major axis. Okay, the major axis is the longer one, and the minor axis is the shorter one, or the smaller one. And then c equals a squared minus b squared. Okay, c, I'm just going to tell you, c equals the distance between the foci, oops, that's terrible, and the center. So we haven't talked about how do you find the equation of, the coordinates of the foci. The foci, you're going to find the coordinates of the foci, remembering that they always lie on the major axis, to this little mini equation. C equals a squared minus b squared. Okay? So let's think about this quickly. Let's do a couple quicker problems. So in the ellipse, x squared over 9 plus y squared over 16 equals 1. What are the values of a and b? And what is the value of c? Okay, i.e., how far away from the origin are the foci? Well, let's take a look at this. What number is larger? 16 or 9. 16 is clearly larger since it's underneath the y. This tells you it's a vertical ellipse. Okay, we don't really need to know that in this case, but it's always good to practice. A value is always underneath the a value is always the larger of the two numbers. So if I know that 16 is a squared, that must mean a is 4. Must mean b is 3, since the number underneath the x squared is b squared. So I know this is a vertical ellipse with an a value of 4 and a b value of 3. And then my foci, the c value, okay, would be the square root, okay, of 16 minus 9. Notice it was b squared. If we scroll back up, a squared minus b squared. Sorry, the 16 and the 9 are already a squared minus b squared. So we don't need to square 16 and 9, which means we have root 7. If we were to draw this out real quickly, I know it doesn't ask us to, because the 16 is below the y. I know it's a vertical ellipse. Okay? I know that the vertices are always the a value. So in this case, the vertice would be 0, 4, and 0, negative 4. The co-vertices would be 3, 0, and negative 3, 0. And the foci are always going to lie on the major axis. The major axis connects the vertices, so I know it's going to be the y-axis here. So the foci, okay, always need to be inside the circle. Since C is root 7, that's the distance between the foci and the center, or the foci and the center. So my coordinates of my two foci would be 0, comma, root 7 and 0, comma, negative root 7. Now you didn't have to do that stuff on the right, you just had to find A, B, and C, but that's going to hopefully give you a better sense of what exactly that means. Try number, actually no, don't try number 2, let's do 2 together. So it says in the ellipse 4x squared plus 9y squared equals 36, what are the values of A and B? What is the value of C, and how far away from the origin are the foci? All right, again, remember, my equation always has to be equal to 1. So what do you think I need to do to the equation 4x squared plus 9y squared equals 36? If you guess divide it by 36, so each side equals, or so the right side equals 1, you are correct. So if I divide both sides by 36, okay, I get 4x squared over 36 plus 9y squared over 36 equals 1. I can simplify this to x squared over 9 plus y squared over 4 equals 1. That is an equation of ellipse that makes sense to me. Okay, that's an equation of ellipse that makes sense to me. So in this case, my A value is always going to be the larger of the two numbers, okay, which is 9. That's the A squared. So my A value would be 3. My B value, okay, would be 2, 4, the square root of 4. And my C value would be root 9 minus 4, which is equal to root 5. Again, that's also the coordinates of your foci. All right. All right. Take a shot at number 3. It's a little bit tricky. If you need your calculator, use the calculator, but try your hand at number 3. And then go from there. And then, so pause the video, try number 3, and then once you think you've got it, or you've gone as far as you can go, hit play and I'll walk through the solutions here. Okay, so hopefully you've given it a shot. What we're going to do here again is I don't like that 441. I need that right side to be 1. So I need to divide both sides by 441. And if you do that, you should be able to simplify the left side to 4 over 9 x squared plus 4 over 49 y squared equals 1. Now again, I only can have an x squared and a y squared in the numerator. Okay, you cannot have a coefficient in front like I have the 4s right now. So what I'm going to do is to rewrite this as x squared over 9/4. Again, if you do same change flip, you should get 4x squared over 9. I'm just rewriting it with a fraction in the denominator, which normally I would say don't do, but you'll see why in this case it's helpful. X squared over 9/4 plus y squared over 49 over 4 equals 1. So again, that's the same thing as the equation above. I've just rewritten it such that I only have a number in the denominator. The larger of the two numbers is your A. So my A is 49 over, or my A squared, I should say, equals 49 over 4, which means A, if I square root it, gives me 7 over 2. So you can see why I rewrote it with the fraction just in the denominator. My B squared equals 9/4, which means my B value is 3 over 2. And my C value is going to be root 49 over 4 minus 9 over 4, which is root 40 over 4, or root 10. Okay. Now again, think for a second, is this a vertical ellipse or horizontal ellipse? Well, the larger value is underneath the y, so this would be a vertical ellipse. All right, then the last problem before I let you guys go. Number 4, find the equation of an ellipse that has a major horizontal axis of 6 and foci at negative 2, 0, and 2, 0. And then what is the eccentricity? That's the word eccentricity. We haven't talked about it. Okay, I'll get to eccentricity in a second. Let's come up with the equation first. All right, so if the major horizontal axis has a length of 6, okay, if it's a horizontal ellipse, okay, and the major axis, okay, is 6, that length there is 6, I know that they're split down the middle by the center, so that point there must be 3, 0, and negative 3, 0. If the entire length of the axis is 6, major axis again being the length or the distance between the two vertices. So in that case, I know that my A value must be 3. Okay. I also know that my foci are at negative 2, 0, and 2, 0, meaning my C value is 2. So again, to find your B value, let's use my little formula. C equals A squared minus B squared. I know 2 should be equal to root 3 squared minus B squared, which if we square both sides, we get 4 equals 9 minus B squared. We get B squared equals 5. You don't necessarily need to find B, but B equals root 5. So I know this is a horizontal ellipse. I know my A value is 3, and my B value is root 5. So since it's horizontal, I know the larger of the two values of the A squared is going to go underneath the X. It's going to be X squared plus 9 plus Y squared over B squared, which is 5, equals 1. So there's my equation of my ellipse. Now, eccentricity just means how thin or fat this oval is. The higher the eccentricity, okay, the skinnier the oval is, the larger the eccentricity, the fatter the oval is, okay? So how do you find the eccentricity? It's a pretty simple formula, okay? Eccentricity is just C over A, okay? C over A, which in this case can easily be found as 2/3. We'll talk a little bit more about eccentricity later on in class tomorrow, but just for right now, know that the eccentricity formula is C over A. All right, so give it your best shot. I'll go over the homework, what that is in a second. It's a little bit tricky. We're going to spend a couple days on this. We're also going to look at ellipses not centered at the origin, which once we've kind of got this ellipses at the origin down, moving them around is not going to be that hard. All right, so for homework, let's do A and B. Okay, so sketch each ellipse, find the coordinates of the foci, state I'm just looking through what these problems are. Let's do B, 6B, 6B, and let's do 7A and C. Okay. So your homework, just to review, is going to be 5A and B. I like the title. I must compliment myself on elliptical workout. 6B and 7A and C. So try those. If you get them, great. If you struggle with them, write down your questions, your specific questions, and we'll go over them in class tomorrow.